Hey y'all, today we're going to be doing a significance test on two sample proportions, trying to find out if we have a significant difference between those two proportions. So let's take a look. You'll recognize this is the exact same problem as the last video. In the last video, we approached this problem using a confidence interval, which was an okay way to do it, but this is a more formal method, which will give us a definitive answer of do we have significant evidence of a drop in favor or not. So just to review what the problem is about, we are running a campaign for governor. We look at we send out a survey to some potential voters, and we find 223 out of the 415 people surveyed support the new candidate. A few weeks later, we do a new survey, and it looks like our love for the new candidate has changed a little bit. So just to wrap up all the information we've been given. The first sample was 415 people were surveyed. 223 of those preferred the new candidate. So we have a proportion of about 54%. In the second sample, we have something closer to 50% of people who favor the candidate. So we're running this campaign. We're a little bit worried that our candidate is going to lose favor. There's about a 3% drop here. So we want to know, is that 3% drop, is that something significant that we should worry about, where this means that people are not liking their candidate as much, or is this little bit of change just due to random chance? So the problem says, do these data support the conclusion that there was a decrease in voter support? So we're specifically looking for a decrease, not just a change. And we're going to provide some statistical evidence for that. So we'll be able to actually say yes or no with some scientific evidence. Okay, so I've collected some of the information given, and I also did this right here. So this is called the combined proportion, sometimes called the pooled proportion. This is just a combination of the two samples. So we're going to be kind of assuming, our null hypothesis is kind of assuming that these two samples are sort of from the same population, that there has been no change, which means we can use this information to provide us basically one really big sample to give us our best estimate of the true proportion. So you'll see that when we do some of these calculations, and you'll see on the formula chart that a pooled proportion is preferred, gives us a better estimate of the true proportion if these were the same sample, if these were from the same population. We're going to be using the calculator for our math today, so we're not going to worry too much about this, but you'll see that in the book. That's what that P hat C means, the combined proportions. Okay, with all inference methods, we always want to follow our four-step process. So we start by stating what we're going to do. So we want to test the null hypothesis. And in this case, our null hypothesis is that nothing has changed, that the amount of people who favor the new candidate, the first sample versus a few weeks later, is exactly the same. So there's two ways we could say that. We could just say that P1 equals P2, and that would be fine. Another way to do it is what I've done here, which says the difference of P1 and P2 is 0. Either one's correct, but I'm going to do it this way because of my upcoming alternative hypothesis. So the first explanation is that the proportions are the same, the difference is 0, and that this change is just random chance. That's explanation number 1, the alternative, the assumed explanation. Explanation number 2 is that less people like our new candidate, that the proportion, the true P1, is actually higher than P2. In other words, if we subtract P2 from P1, we'd get a number bigger than 0, meaning P1's bigger. So we're going to be testing this at a significance level of 0.05. If you're not given a significance level, then this is sort of our default choice. If we find out that this was going to happen with a likelihood less than 5%, that is statistically significant. Okay, and we also want to define what do we mean by P1 and P2. P1 is the proportion of voters who like the new candidate in the first sample. P2 is for the second sample. Okay, after we've stated what we're going to do, we want to plan it out, and that means we need to check our conditions. There's pretty much always the same 3 conditions we're checking for these inference methods that we're looking at. We want to know, are our 2 samples random? So notice I did name the test we're doing, a 2-sample z-test, or you could call it a 2-proportion z-test. We're allowed to do that as long as we have 2 random samples. Should not have said the word independent here. Sorry, cut that out. Just 2 random samples were taken. In the prompt, they tell us a random sample, a random sample. So we're good. Notice I am checking for both samples. You do have to check both. We need to know, do we have independence? It's not super clear what's going on from the prompt. Most likely we're not interviewing the same potential voter twice. So we probably are not sampling with replacement, but we can sort of ignore that as long as our two sample sizes are less than 10% of the total population. Basically, this assumption that we're going to go with, saying that 415 is probably less than 10% of all the voters in that state. That's a safe assumption, I think. And doing so means that when we do our calculations, the difference between sampling with replacement and without is going to be so small that we don't really care. So we're going to go ahead and assume independence based on sample size being much smaller than the population. The last thing we want to check is the large counts condition. We do large counts when we're dealing with proportions, and that's so that we can make sure that the sampling distribution of our proportions is approximately normal. So the large counts looks like this: is n times p greater than 10, and also is n times 1 minus p greater than 10. So we've seen this a lot in previous chapters. The only difference here is that we're doing it for both samples. So you need to check for P1 and P2. Notice it's P hat because we're looking at the actual sample proportions. Okay, so I've checked these conditions. We've said N1 times P1 is greater than 10. 415 voters times about 54% is much bigger than 10, so we're safe. So this is the way that we've gotten used to doing this, and it's a great way to check. Notice that we have every sort of conditional value is greater than 10. So I like to show the math, n times p is greater than 10, but you could also just make like a little two-way table and just show that we have 223 voters said yes in the first sample, 192 said no. Those numbers are greater than 10, so we're good. But I like to show the math just because it's pretty straightforward and it's what we're used to. Okay, now we can actually go ahead and do some calculations. So we said what we're going to do, we made a plan, we checked some conditions, now we want to actually do the math. So this math can be done by hand. If you look at my 10.1 notes, you'll see that I've done the whole thing by hand a couple times on there, but really the calculator is probably your best bet here. It's really straightforward, prevents you from making little arithmetic errors, and well, it's just easy. So we go into our stat menu like we always do, and then we go over to tests, and what we're looking for is a 2 proportion z test. All right, again, 2 sample z test, or a 2 proportion z test. Okay, so when we go in there, we want to enter all of our data. So our first sample was 223 successes out of 415. Sample number 2 was 317 successes out of 630. And then we also want to say what the alternative hypothesis is. Most of the time, we're actually doing P1 is not equal to P2. That's what you're going to see most of the time. But in this situation, it's a little bit different. We're looking for a decrease in voters. So we're actually saying something like this, that P1 is bigger than P2. So be careful, make sure you've set your alternative hypothesis to the correct condition. Okay, now we can go ahead and calculate this. So we click calculate. The calculator is going to give us a lot of information here. So the most important things you're going to get out of this output is the z-score and the p-value. P-value in the calculator is just called p. So our output, I'm going to write down that z is 1.08 and that our p-value is 0.14. And then all this other stuff we already have written down. We got P1, we wrote that down at the beginning. P2 is written down here. P hat is the combined P, and they also give us sample size. So all that other information we already have written down. We just want to make sure we get the P value on the page, and that's super important. This is the main thing we're looking for. Remember, the P value tells you how likely is this difference going to happen, assuming the null hypothesis is true. So I would encourage you to pause the video right now and see if you can write a conclusion and decide, what does this p-value tell us? What can we decide based on that p-value? All right, let's write our conclusion together. So what this is telling me is that if I were to find the difference in these two proportions over and over and over again, the chance that we would have a difference of about 3.5% when actually those two proportions were the same, and that change, that 3.5% drop, is just due to random chance, the likelihood of that happening is about a 14% chance, right? Or 0.13968. So it's not super likely that that would happen, but it's not so unlikely that it's unheard of, right? A 15% chance is pretty low, but not quite low enough based on our significance level. So this is what our conclusion would look like. So we've decided our p-value, 0.14, is actually larger than alpha. So we were going to say this was significant only if the chance of this happening was less than 5%. We actually found out that the chance of this happening just due to random chance is 14%. So that's bigger than alpha, so we fail to reject the HO. There is not sufficient evidence that the proportion of voters who support the new candidate has decreased since the first sample. Maybe it did. Maybe it actually did drop off a little bit, but based on these samples, we don't have significant evidence. That little bit of a drop, that 3.5% change, could be due to some weird remarks that the candidate made, or could just be random chance. There's about a 14% chance that that just happened by accident. Cool. So that's our 4-step process. I want to take a little bit more time on this video to kind of visualize what we just did and talk through it again, because I know you can get a little bit bogged down in the math and the steps and all this stuff and kind of forget what this is telling us. So to visualize this, the first thing I'm going to do is look at what does the sampling distribution look like given the null hypothesis. So remember, our null hypothesis is that these two proportions are the same thing. So if we have a population of voters, right, all the voters in this state, and truly about 52% of them support the new candidate. And again, that number is our combined proportion, which is our best guess as what the true proportion is if there is no change. So if the true number of people who support this new voter is around 52%, what possible proportions would we get if we took a sample? So you'll notice I've also got my standard deviation. If you're really confused about how I figured out that standard deviation, you can take a look at your formula chart. So for two populations, this is on page 2 of your formula sheet. For two proportions, if we're assuming that P1 and P2 are the same, then we use this formula. Again, notice you're using the pooled or the combined proportion for that. So all these formulas do exist on our formula sheet, but again, the calculator is the way to go here. All right, so what this histogram is showing us is basically all the possible proportions that we would see if we drew out of all the voters in the state. The red line shows us what the true proportion is, about 52%. So if we took a sample of voters, most likely we're going to get a value really close to the real value, the real proportion of 52%. But it's possible that taking a sample, we could get something like 60%, or even as low as 45%. So there's some variance involved. There's some random chance that happens when we take a sample. The sample isn't always going to be super truthful. As we increase sample size, it gets more and more centered around, or less spread around that center. But we do see some variance at this level. So it's possible some of our samples are kind of bad. Now, if we take this idea of visualizing and doing some simulation a little bit further, we can actually do the same process that we just did in our hypothesis test. So again, I'm showing you a lot of code here just for fun, but you don't have to understand or follow this. But hopefully you can see the basics of what's going on here. So what I'm going to do here is I'm going to take a sample, a single sample from this distribution, where we have a mean at this red line of about 52%, and the standard deviation is based on the first sample size, 415 voters. Cool. So I'm going to take my first proportion from that sample, and I'm going to take my second proportion from a second sample from the same exact population, and then I'm going to return the difference in those. So I'm going to take a proportion, take a second proportion from the same population, again, assuming that they're the same. So this is under the assumption of the null hypothesis. I'm going to find the difference. And then I'm going to take those differences, I'm going to repeat that 10,000 times. So take a sample from the population, find the proportion. Take a second sample, find the proportion, and then subtract those. And then I'm going to repeat that process, replicate that process 10,000 times. So when we do that, we get this histogram. So most of the time, we have a difference really close to 0. There isn't supposed to be a difference because both of those proportions were pulled from the same population. So most of the time, we're going to see no difference at all. But sometimes you get unlucky, right? Sometimes P1 was one of these large values, and we get a difference of 5 or even 10%. Those are pretty rare. Or maybe P2 was bigger, right? 5% or negative 10% or 10% the other way. This red line represents our sample. So in our sample, we had a difference of about 3.5%. So we can see that in the grand scheme of things, our sample was a little bit unusually high. We do see a pretty big difference that isn't really likely, but it's not super far off in the realm of possibilities. So hopefully that visualization helped you understand kind of what the process of a significance test looks like. And actually, if we take these 10,000 samples and actually calculate how many of those were above this red line, we get about 15%, which is really similar to what we got when we did the theoretical. We got 14%. So pretty similar in our simulation. Got pretty much the same value. If we ran this again, we'd get another value really close to that. Cool. Thanks, guys. I hope you have a great week. Next video coming soon.